So when it comes to forces on the inclined plane, there's really only one big one you have to keep in mind when it comes to without friction. With friction, of course, we have to account for friction, which is a non-conservative force, so that changes things somewhat. But when it comes to gravity, I think it really, before we actually tackle solving these, it's important to understand what's actually going on, right? So I think first, to really get into this, we kind of need to understand this a little bit more, right? So here's a horizontal plane. We have gravity just pushing straight down, or we can say that it's pushing perpendicular to the surface. And so what is gravity really trying to do here, right? It's obviously trying to push this down, but what does that mean? It's trying to create motion, and the only motion that's possible in this manner is if the object was able to slide through this surface, right? And we know that that's not going to happen here, just due to whatever the properties of that material are, which properties and stiffness and elasticity and all that. That'll be covered later in physics, but for now we're not concerned about that. So we're just going to say that it is sufficiently strong enough to withstand that force, and because of that, it'll exert an equal and opposite normal force, which can be denoted as such. For most of the time, we're just going to use N, which we know is equal to mg, which we know mg is just w, but we're going to keep it in mg a lot of the time because that'll be just more useful to us than just plain old w, right? So again, we know that gravity is just trying to push whatever is on top just straight down, right? And because it's a flat plane, we know that this normal force is going to be, just equal and opposite, wholly perpendicular, right? And again, that's kind of key here. You want to think of perpendicular and parallel. So with an inclined plane, right, obviously it's being tilted by some angle theta, right, relative to the ground. And so gravity, it's important to note, is still just pointing straight down, right? It's still just pointing perpendicular. That's not changing. The normal force is also just pointing straight back at gravity, right? That's not changing as well. So the actual behavior, of course, isn't changing. That's not really helpful for us, right? If we want to calculate things, we want to break it up into vectors, right? We know that from kinematics, if we have some guy and he translates over to A, right? We can represent that in terms of X, in terms of the Y component, right? So we want to do the same thing, right? Because we know that Newton's second law, force equals mass times acceleration, is actually, the sum of the forces in the X direction and the sum of the forces in the Y direction, right? So there's an X and a Y component with forces as well. And that's really a lot more useful to us. So how can we kind of break gravity as it relates to the force it exerts on the surface and the force it exerts on the object, which then exerts force on the surface? How can we break that up into an X and Y, right? Well, instead of an X and Y, we're going to think of perpendicular and parallel, right? So gravity is going to go perpendicular to the surface just like that. And then that's going to be the perpendicular force it's exerting. And then there's going to be a parallel force, right? It's going to travel along the surface, which we say is parallel, right? So we want to represent that with a force triangle, right? Because we do love triangles in physics. Those are very helpful for us. So we want to think of gravity, also traveling along some parallel axis, right? And I think you can kind of already see it from here. If we just complete this, make a little triangle, right? Nice and tidy. We know that this parallel axis has to have been, rotated and adjusted to keep parallel the same degree as the ramp itself was lifted up off the ground, right? So knowing that, we can then kind of determine using the angle, well, what's going to be our opposite and what's going to be our adjacent here, right? Well, this angle here, right, again, is going to be, very similar or identical to this angle here, just using geometric theorem. And again, this is supposed to be a right triangle, so just kind of ignore my poor drawing. But this is going to be our adjacent side, right here, and this is going to be our opposite side. And what's associated with opposite? Opposite is from SOHCAHTOA, sine, and we know adjacent from SOHCAHTOA, sorry, is cosine theta, right? So now we have kind of a way to break gravity into different components, right? Using this little force triangle here, we know that the perpendicular force is going to be our adjacent, so cosine theta, and we know the parallel force is going to be sine of theta, right? So we'll get rid of all that now. Kind of clean this up. So now, knowing how the forces kind of decompose, and it kind of makes sense when you think about it, right? Because if we have, again, gravity pointing straight down, right, on a horizontal plane. The angle that, you know, the inclined plane makes with the ground, well, you know, it's exactly overlaid with the ground, so our theta is going to be 0. So our mg sine of theta, right, should be equal to 0 as well, because sine of 0 is 0. And our mg cosine theta, right, is going to be using a multiplier of 1, right? Which makes sense because the force pushing straight down is maximal, right? There's nothing pulling the object this way and this way at rest, because of course the gravity is just straight perpendicular, right? There's no parallel component here. It's fully perpendicular, so we basically just assume that mg sine of theta is non-existent here, do not have to factor it at all. But, you know, then we start, you know, raising the inclined plane somewhat, right? We have some pretty small angles, say it's like, I don't know, not even 20, like, let's say like 5 degrees, right? Well, the object is still like mostly getting pressed by gravity into the surface. It's just now slightly being pulled by gravity downward, right? Along the parallel axis, right? So now there is some contribution from mg sine theta, right? Because it's not purely perpendicular anymore. And then of course, as our angle increases, right, sine theta is going to get, you know, it's going to keep going up, while we have our mg cosine of theta is going to keep going down, right? Because again, mg cosine theta represents how much the object's pulling or pushing into the surface by gravity, and then mg sine theta is representing how much it's getting pulled by gravity along the axis, right? And then you think about, you know, what if we had just a straight vertical inclined plane, right? Well, then we know that the object isn't even really being pushed by gravity anymore into the surface, right? It's just, you know, traveling parallel to it. So the contribution from mg cosine theta at this point at, you know, mg cosine 90 degrees would be, of course, 0, because cosine of 90 degrees is equal to 0. So that all makes kind of physical sense as well when you think about it. So now let's actually approach solving problems with some values, right? So we can see here that we're given a mass of 10 kilograms, and we have a theta for the angle, which is 30 degrees, and then the distance from the point of rest to the end of the ramp is going to be 8 meters, right? So for question 1, how much of the object's weight is pressing into the surface? So we know again that the pressing into the surface is going to be dealt by the perpendicular axis, which again is going to be adjacent, and we know that adjacent is cosine of theta, right? So we're going to use mg cosine of theta to solve this. So we do the mass times acceleration due to gravity times cosine of 30 degrees, which we know should be about the square root of 3 over 2. We take our calculator out, do 10 times 9.8 times cosine of 30, right? We're going to get 84.87 newtons, right? 87 newtons. So now how much of the object's weight is trying to pull it down the ramp? And again, this doesn't make sense because, you know, when you think about it, 30 degrees isn't that much to lift it off. This, you know, is not exactly thrown to scale. 30 degrees would be, you know, a lot less steep. So that makes sense. Most of the weight is still pushing against the surface, right? But if we ask how much of the object's weight is trying to pull it down the ramp, then of course, if we're talking about pulling it along, we're talking about the parallel axis. We know the parallel was opposite, so we use mg sine of theta, right? And then of course that's going to be equal to 10 times 9.8 times sine of 30 degrees, which you know sine of 30 should be about 1/2. And that'll be equal to just, you know, 10 times 9.8. It's going to be 98 times 1/2 is going to be 49 newtons. And, you know, you can fact check that if you want, but should be right. 0.5, 49 newtons, right? And so now we take these and we're going to do, you know, some vector addition to find and make sure that it makes sense, right? Because, of course, we know that the just general weight of the mass should be 98 newtons, right? Because it's 10 times 9.8 without any trigonometric functions. So the vector sum of these should be 98 newtons. So let's do 84.87 squared plus 49 squared, 9603. And then we're going to square root that answer, and we get 97.909, which we can, you know, just approximate to 98 newtons, right? So that all makes sense. That's all well and good. So now let's tackle problem 3, right? What's the acceleration of the object down the ramp? Well, let's think about what's involved with the acceleration of the object, right? So if the object's accelerating down the ramp, well, what's the, number one equation we can use in this situation, right? We can use force equals mass times acceleration. But if we're talking about down the ramp, right, then we're talking about parallel to the ramp. What's parallel to the ramp? Well, we know that that was mg sine of theta, right? So the force that we're going to be concerned with is 49 newtons. But of course, let's kind of do this symbolically and kind of approach that way. So force equals mass times acceleration. What's the force here? It's going to be mg sine of theta. So we replace force with mg sine of theta, so we don't even need any values yet. Let's just purely think of this, and equals mass times acceleration, right? Well, do we see anything here we can cancel, kind of get rid of? We know that there's an m on both sides, so we can kind of just get rid of that m. And that leaves us with g sine of theta equals a. So now all we have to do is plug in 9.8 for g times sine of 30 degrees. And then again, we knew sine of 30 degrees is just 0.5 or 1/2. So it's literally acceleration is just 9.8 times 0.5 or 1/2 equals a, which we know half of 9.8 is just going to be 4.9. So the object's going to accelerate for 4.9 meters a second down the ramp, right? Meters a second squared. That's going to be its acceleration. So now that we have that, that kind of opens us up to being able to, solve some other basic kinematic questions, right? So what's the final velocity of the object at the end of the ramp? Well, again, we know that the distance to the end of the ramp is going to be 8 meters, right? But, we don't have time, so we have to kind of think about, well, what equation can we use for this? We know we have final velocity as a function of time for constant acceleration. We know we have position as a function of time, and we have velocity as a function of position, right? So since we don't have time, we probably want to use velocity as a function of position, right? And we know the equation for that is going to be the final velocity squared equals the initial velocity squared plus 2 times the acceleration times delta x, right? So then we're going to go ahead and assume that, since it begins from rest, the initial velocity should be 0. So we're going to say this just cancels out. So we're going to have 2 times our acceleration along the ramp is going to be 4.9 meters a second squared. And we know that our displacement starts here. It's going to end at the end of the ramp is going to be 8 meters. So we know our displacement 8 minus 0, which is just 8. So we know that we can replace that with 8. So then we just do 2 times 4.9 times 8 is 78.4. So we're going to get v squared final is going to be, 78.4? And we know now that to find the velocity, the final velocity, vf, we need to get rid of that square, so we have to square root it. So we square root both sides. So square root 78.4 is going to be 8.85. So we'll round it to meters a second, right? So get rid of all that. And then move that over here. So now that we have the final velocity, can't we find the time? So how long does it take for the object to reach the end of the ramp? Well, we can just use velocity as a function of time. So we know vf equals v initial plus acceleration times time. And we should have the vf, so we plug it in here, 8.85, or rather we should first isolate this for time. I think it'd be a lot simpler. So vf minus vi equals at, then get rid of the a, so it should be vf minus vi over a equals t, right? And now all we have to do, plug things in, so t equals 8.85, we start from rest, so it's 0, over acceleration, which we again know is 4.9, since we're talking about acceleration along the ramp. So 8.85 minus 0 is 8.85 divided by 4.9 is 1.806. So it should take about 1.81 seconds, we'll round up, seconds for the object to reach the end of the ramp. And that's really about as difficult as I would say it gets for just simple inclined plane problems without friction. So the next video we'll move into covering with friction, and then after that we'll explore solving these problems with work energy theorem, which is personally my kind of go-to for solving these. You don't have to deal with all these extra factors, but I think it's important to understand this just to understand what's happening. But personally, for me, I just prefer using work energy theorem. It's cool and a lot more fun for solving these. So that'll conclude these. I will see you in the next video.